So next we discuss the complex scalar field, and I'm going to introduce it in a way that is makes sense to me. Others introduce it in different ways. So let's take a theory where we have two real scalar fields of mass m1 and m2 of mass term. So this, well, we can now call the mass term mass because we have seen that, we have particles. So suppose we have two scalar fields, one with mass m1, another one with mass m2. So the first one is half the Lagrangian is, we call it phi1, and the mass term is m1 squared by 2 phi1 squared. And then the second field, we add the Lagrangian, will be, the second field is denoted by phi2, and its mass is m2. Now, in the limit, when m1 is equal to m2, and we call it m, what we can do is that we can combine these two scalar fields into a complex scalar field. So let's write this as phi1 plus I phi2. And then we can express this Lagrangian as a Lagrangian of a complex scalar field. Like this. Note that we could not have done it if the masses were different. Then the mass term would not neatly add up like this. This term would, but the mass term would not. So this limit was important. So this is what I'm calling a complex scalar field, or a complex Klein-Gordon scalar field. So, when we quantize this theory, the Lagrangian will become del mu of phi dagger, del mu of phi minus m squared phi dagger phi. Now, note that phi is not a Hermitian operator. This is not Hermitian. So in quantum field theory, we are mostly used to Hermitian operators. So rest assured that all the observables that you can make out of theory are going to be Hermitian. So there'll be combination of phi and phi dagger in such a way that the result is Hermitian. So now we can express the mode expansion, say the classical mode expansion, for example, of such a scalar field, a complex scalar field. And it's going to have the form. So this is the relativistic, the invariant measure. And then we'll have a of k e to the power minus I kx. These are called the positive frequency modes. And then we'll have some other term, say c of k e to the power I kx. Now, because we are not required to impose the reality condition on this scalar field because it is not real, so we are not required to do this. That means that this coefficient and this coefficient need not be the same. But a careful analysis of this theory shows that while A will have an interpretation of an annihilation operator, this guy will have an interpretation as a creation operator. So, because of that, it's usually written, we don't write it as A plus C, but we write it something like A of K e to the power minus I kx plus b dagger of k e to the power I kx. So this is the Fourier mode expansion of a complex scalar field. The canonical commutation relationship of the complex scalar field, now you can derive those from the real scalar field, or you can impose them, and they turn out to be the equal time commutator between x and its canonically conjugate momentum is going to be given by the usual, as well as its Hermitian conjugate. So in the Hermitian conjugate, all of these things would be Hermitian conjugate, and there should be a minus sign on the right-hand side. So all other commutation relationships, such as phi and phi, as well as phi and its conjugate, pi, pi, they will all vanish. And it can be shown by doing a Fourier transform of these relationships that they are equivalent to the A dagger commutation relationships being the usual ones, as well as the B daggers. They also satisfy similar commutation relationship. And all the other ones, such as, say, AA, then A dagger, BB, then B dagger, and the next one where you have A and B dagger, etc., etc. All of these guys vanish. So as I said before, the easiest way to see this commutation relationship is to start with the canonical commutation relationships of the two real scalar fields, phi1 and phi2, and then take the linear combinations and see what comes about. And you have to remember that phi1 and phi2, they're like, different, the position operator of, say, different particles in quantum mechanics, and therefore, they will commute. So what would be the Hamiltonian of such a theory? So also, it's not very hard to figure out. The Hamiltonian of such a theory will have the usual Lorentz invariant measure times the energy eigenvalue, and then it'll have the number operator associated with the A operators and the number operators associated with the B operators. And this shows that we can think of the A operators as creating an A-type particle and the B operators creating a B-type particle. And in the next lecture, we shall see that A and B-type particles can be interpreted as antiparticle of each other. So if A is a particle, the B particle would be the antiparticle. It'll have the same mass, but opposite charge. So similar to the real scalar field, if we apply, say, the A operator a bunch of times, and the B operator, say, also a bunch of times. So the A operator is being, A dagger is being applied n times, and the B dagger is being applied m times on the vacuum. Then we're going to get a state which has n of the A particles and m of the B particles. So several things we should note. From the expression of the Hamiltonian, see, the Hamiltonian had a form of some integral times A dagger A plus B dagger B. From the form of these number operators, we see that the Hamiltonian is a positive definite operator. That is, the expectation of the Hamiltonian is going to be positive. So that was number one. And number two is that, because of the absence of this condition for the complex scalar field, we can have in the Fourier expansion two types of operators, A and B, and of course their Hermitian conjugates.